Hello everyone, I'm Professor Harrison, and welcome back to our module on Calculus for Finance. Today we're going to be covering comparative statics, which is how the optimal solution to an optimization problem responds when one of its parameters shifts. We're following Victor, a fund manager whose edge is slipping and he can't figure out why, corresponding with the rational quant. His fund has been losing money lately in ways his sensitivity calculations don't account for. He opens the latest letter from his anonymous correspondent. In an optimization problem, there's a subtle but important distinction between the things you choose and the things that you take as given. The thing you choose is called the decision variable. The things that you take as given are called parameters. You're picking the decision variable to maximize or minimize some objective, and that choice depends on what the parameters are. Comparative statics is the study of how those optimal choices change when one of those parameters shifts. The simplest method, which we'll call the direct method, is two steps. First, we set up the optimization, and then we take the derivative of the objective with respect to the decision variable and set it equal to 0 in order to find the critical values. Solving this gives you the optimal decision as an explicit function of whatever your parameters are. Then we can again take the derivative of that function, which in some sense is the second derivative, but the difference is that this time we take the derivative with respect to the parameter. This result is the sensitivity of the optimal solution to a small change in the parameter. This sounds confusing, but let's work through a simple example. Suppose a small firm picks the quantity it produces, Q, to maximize its profit. The market price the firm faces is P. The firm doesn't control the market price, so it takes P as given. So Q is the decision variable and P is the parameter. Profit is revenue minus cost. So revenue is price times quantity, P times Q, and we'll use a quadratic cost of Q squared, which ends up being a clean stand-in for any cost that rises faster than linearly. So profit as a function of quantity for any given price is P times Q minus Q squared. Now we apply the first order condition. The derivative of profit with respect to Q is P minus 2Q. Setting that equal to 0 and solving for Q, we get that Q star, the optimal quantity to produce, equals P over 2. That's the optimal quantity at any given price as a function of the price. Now here's where comparative statics actually happens. We have Q star written as an explicit function of P. So we can take the derivative of that function with respect to P directly. dq star dp equals 1/2, and that's the answer. The optimal quantity rises by half a unit for every dollar of increase in price. Let's plug in some numbers to verify. Suppose P equals 20, then Q star equals 10. Now suppose the price raises up to $22. Plugging in Q star equals 11. The change in the optimal quantity is 1. And the change in the price is 2, and the ratio is 1/2. Since market prices tend to fluctuate, and they usually are something that is taken by the firm, this gives an actionable plan for the firm to react to whenever prices change. They know that by however much prices go up, they just have to increase their quantity of output by 1/2 of that in order to stay at the optimum. Comparative statics is what gives us the formula to allow this decision rule to take place. Victor puts down the letter. Today he's sizing a single equity position in his fund. The question he wants to answer is how much his optimal weight in that position should shift when his forecast for the position's expected return shifts. In notation, that's dx star d mu, the derivative of optimal weight with respect to the expected return. The position sizing formula gives weight as a closed form function of expected return, so the direct method works cleanly here. For a single risky asset against a risk-free position, the optimal weight under mean variance preference is mu over gamma sigma squared, where mu is the expected return, sigma squared is the variance of returns, and gamma is his risk aversion coefficient. Basically, gamma measures how much variance he's willing to tolerate per unit of expected return. The variance and risk aversion are taken as constants in this calculation, and the parameter that we're going to vary is mu, the expected return. So Victor applies the direct method. Take the derivative of x star with respect to mu. The variance and risk aversion are constants, so the derivative ends up being 1 over gamma sigma squared. Plug in his numbers. His risk aversion coefficient is 4. The asset's volatility is 20%, so sigma squared is 0.04. Gamma times sigma squared is 0.16, so the sensitivity ends up being 1 over 0.16, which is 6.25. So for every percentage point Victor adds to his expected return forecast, his optimal weight in the asset rises by 6.25 percentage points. If his forecast is 8%, then the optimal weight is 50%. If his forecast bumps to 9%, then the optimal weight rises to 56.25%. After this calculation, Victor turns the same tools on his fund's recent losses, computing what the profit and loss should have been given the parameter movements that actually occurred over the last 6 months. His actual losses are much larger than the sensitivities account for. To figure out what's going on, he pulls the counterparty records from his latest losing trades, and he finds that the rational quant was on the other side of every single trade. He decides to sit down and write a letter to his anonymous correspondent to figure out what's going on. So that's comparative statics. The procedure is 2 steps. First, solve the first order condition for the optimal decision as an explicit function of the parameter. Then take the derivative of that optimal solution with respect to the parameter. That derivative is a sensitivity slope that tells you how the optimum responds when the parameter shifts. It's one of the tools that ends up being the most useful in actual finance work, because almost every model has parameters that you can never pin down exactly that you have to take as given.